we are heading over to the next presenter, Erik. Welcome, Erik. Erik is a software developer and passionate technologist. Erik is head of technology at Thoughtworks. He helps clients solve their business challenges using modern technologies, platform, and practices. Welcome very much, Erik.
Yeah, thank you so much.
You're welcome.
That's going to be a tough presentation to follow up on. I don't know your audience that well. This has going to be a lot of code in the coming one, but I'm going to present Rust more from a broader perspective. So I hope that's going to be applicable to you. I'm a consultant, so I do see many different programming languages. I like Clojure quite a bit. I've even programmed commercially in Clojure. But today, this is about Rust and the different aspects, and especially also the ecosystem. I think we are going to take about 45 minutes for this and then have time for questions at the end. To get started, let me just sort out my screen here. This is always fun. I've given this talk and variations of it for quite a while, and I always have to update this slide. You're probably very familiar with StackOverflow, and they do a survey once a year, obviously, and this is the result from the 2022 survey. They asked lots of different questions, and they ask, what is the most loved technology? And you probably don't have to search very much, but Rust is in the top spot. And funnily enough, it has been in that top spot for 7 years in a row, usually with a margin like that. And what is even more interesting is 2015, 7 years ago, was also the year when Rust actually was released, when the 1.0 version of Rust came out. So that basically means this programming language, for one reason or another, since the 1.0 release, has occupied the top spot on the Stack Overflow developer survey. What is interesting though, and I've done this for a number of years now, when you contrast that with the favorite one, like what people are actually using in day-to-day, and this is the one from 2022, it's not that easy to find. It's a bit further down at about 9% here. This is actually constantly creeping up. I mean, I've done this like 7% last year, and in 2020 it was 5%. But we still see a huge discrepancy here. People who know Rust really love it, but then when we look at how it is being used, what is actually being used on projects, then we see a very, very different picture. My personal belief is that that is because Rust occupies a specific niche. It's very, very good in that niche, but it is not as applicable outside that niche. And hopefully, in the next 40 minutes, I can explain to you why Rust is very good in particular things, but you will probably also see, depending on what you're programming in otherwise and what your problem domain is, that it might not be applicable to what you are doing. So to get us started off, what do these three companies have in common? Apple, Google, and Mozilla. They're all companies that have a dependency on C and C-derived languages, and all three of them had their issues with it to the point where they invented new languages. And Apple went to Swift to replace Objective-C. Google, in some ways, and I know this is not a perfect one-to-one match, they actually invented Go for a lot of the components that run in native cloud applications, and also some of the tooling, obviously, that was particularly written in C and C++. And then Mozilla, of course, has a big browser, Firefox, that was written or is still largely written in C++, and they invented the Rust programming language. Why do these companies do this? Why do they invent new programming languages? Why do they try to get away from C++? This here is a screenshot from the release notes of a version of iOS. I didn't update this one. If I did iOS 16, which came out a while ago, it would very similar. I'm sure I didn't cherry pick this one. If you look, and I guess when you're sitting at home now in this way of a webinar, you can actually even read the smaller text. If you look at that section about color sync, in the description, it says, a memory corruption issue existed in the processing of some profiles and so on. So here we have a memory corruption problem, which is, of course, often a way to exploit, to open up the security mechanisms built into an operating system, be that on a phone or on a computer or somewhere else. And then when you zoom out and you look through these release notes, you can see I've marked them all up. All of the ones with the red dot were something to do with memory management problems that caused security issues that had vulnerabilities assigned to them. And that, of course, is not very good for a platform running on a computer or on a mobile phone. And now you might think, okay, that's an Apple problem. Let's look at another company. Here's Microsoft, slightly older article, 3 years ago. And what they are saying even back then is because they have so many problems with memory bugs, they are also looking at Rust instead. And I don't know how much you've seen about this. Microsoft, of course, has a huge attack surface. They have written a lot about writing secure code, including a very, very thick book that has a lot of good advice. And still 10, 15 years on, they are still having lots of problems. In fact, and this is a quote from a study of a Microsoft Research Center, they say the majority of vulnerabilities that have a CVE number assigned are to do with memory-related corruption bugs. And it is about C and C++. This is not about C++ being a difficult language. Actually, in a way it is, but it is not about the language being difficult. It's just human beings can't write code very well in that space. And it is not for lack of trying. We've really, really tried quite hard. So that is one of the areas why people are saying we need to actually get away from C and C++. Of course, I didn't mention it explicitly. Productivity, more powerful abstractions on the level that we just saw in the talk before are also, of course, a common reason. Personally, I'm coming from a different angle on this one. As a consultant, some of our clients are working with embedded systems, especially in the automotive industry. And here you can see, in comparison to this AA battery, really, really small, very powerful hardware units. And those were often also programmed in C and C++. They become more and more complex. They are in safety critical systems. There's lots and lots of literature about how to write safe code. But again, the contention, of course, is they will land in the same spot that Microsoft found themselves in. They want to do the right thing. They have all these things, but it proves to be so difficult. So they are looking at doing different technologies as well. And here's a press release from earlier this year. AutoSAR is a very, very influential consortium in the automotive industry, and they're also now investigating Rust as a programming language. So there's lots of organizations that have a traditional dependency on C and C++ that are now saying, because of the downsides, we are now looking at Rust as a programming language. So that was a bit of background. To get started with Rust, it's actually quite nice. It does everything that you would expect from a modern programming language, to the point where it is boring. But I think in that case, it's actually a really good treat of the language. You can install it. You can install it also on a Unix-based system completely in your user account. You don't have to install anything in /user/opt or so. It can happily live in your home directory. And you have this central command that I've highlighted up there, rust up, which allows you to also update the entire distribution of the programming language, including the compiler chain, etc. Once you're over that, there's a tool, a package manager, that is also included in the language. I guess most of us expect this now, but even if you only look back to the introduction of Swift by Apple, that did not come with a package manager from the start. Rust did that, and I think it is for the better. The package manager is called Cargo. And what we can see here is has, as you would expect, some scaffolding built in. So I can say Cargo, create something new, a new project, a new piece of software, and I want to call it Hello Rust here. And what we see is very, very minimal, very simple. That is the entire directory structure. It creates a file called toml. That is like the package file, the description of your, we often call them still projects, right? I mean, the description of what to build, and then a simple main file that contains the entry function. So it is actually much, much simpler than what you would expect in many other environments from a scaffolding system. The good thing to know about Rust is also it can and generally is linked statically into a single binary. So unlike Python or Ruby, you can ship the binary around, you have no dependencies, you can compile this, you can have a continuous delivery pipeline, you build one binary, and you can deploy that onto your machine, and it will run standalone. What I'm going to show you later, or all the code examples, are actually from a little hobby project that I did. It is a simulation in the space of artificial life and machine learning. So the idea really is you have a world that has creatures running around in them. Those creatures have to eat or else, because they use energy, or else they will die. That's the basically artificial life part. And the machine learning is not done as a neural network, but through genetic programming. These little creatures do have a strategy encoded in them that describes how they move around in the world. When two of these creatures meet under certain circumstances, they can produce offspring, and then the programs are recombined and the new creature can run around. That's, I guess, if you're not familiar with it, you don't have to be too familiar with it. it's genetic programming, but it's just serving as an example, and I'm not really going to go into too much detail about it. The thing you have to remember is there's going to be a world, creatures are running around in the world, and they're interacting with each other. If you look closely, you notice that I'm showing you a screenshot here of that project, of that software project, but it is not Visual Studio. I'm actually using IntelliJ. Many of you may know these IDEs. They are sometimes called the JetBrains IDEs. They're sometimes called differently for the programming languages. As far as I'm aware, there's not a specific Rust version out, but the, if you will, generic Java version actually works quite well. I tried Visual Studio Code as well, and I found in this case, actually, IntelliJ worked better for me. The refactoring is a little bit more advanced. It doesn't do everything that it can do for other programming languages, but it is actually quite good already. But this talk is about Rust and not so much about the IDEs. I want to highlight a couple of things here. If you look in this package file that I've highlighted here, you can see in lines 11, 12, and 13, I've declared a dependency on another package called cert, which stands for serialization and deserialization. That's interesting insofar that this is not built into the programming language. So Rust is very much in the tradition of C, but also JavaScript, that it doesn't come with a huge standard library. It actually allows you to take different libraries that you want to have, and that would probably, and likely does, allow more innovation, but it also leads to a little bit more confusion. If you look in line 8, for example, I'm including Chrono, which is a date time library. When I first started using Rust, I was really surprised that that wasn't included. And it took me a while, like, I don't know, 10, 15 minutes on the internet to actually decide on which of the different time libraries I should use. So it comes with pros and cons. What is also interesting, if you look at that more closely, you see that cert itself is split. I have a different one for JSON and derive. We probably won't get to what derive is, but JSON is interesting. The default package of cert, the serializer, deserializer, cannot deserialize to JSON. I need to include another one. Here, you can see how Rust is applicable to domains where you want to absolutely minimize the attack surface. Code that isn't in there can't be vulnerable, but also reduce the size of the binaries. If I don't need JSON, if I need another serialization format, I would include that. So I only include what I need. Even more interesting, if you look at the last line, line 14, you can see that the dependencies can actually know about each other. So in line 14, I'm including a dependency to do UUID, unique IDs, and I can see features here. I can say this UUID library I'm using knows a bit about cert, about the serializer, and I want that feature included. So that is actually quite powerful as well, that these packages can express that they have dependencies on each other, which really allows that ecosystem to grow, to have that open ecosystem without a huge standard library, but still provide that path for the libraries to interact with each other in a meaningful way. What I also particularly liked is you can see this in line 5, Rust has named editions. I'm using here the 2018 version of the language, and that will work with future compilers. For those of you, for example, who have done Swift, know how messy that can be. If I open a project that I wrote in Swift 3 years ago, it will not compile in the current version of the toolchain that Apple ships. And sometimes I can't even install the current version or the version of the toolchain on the current operating system anymore. I found myself installing a version of macOS in a virtual machine just to be able to compile code or actually migrate it. That was 3 years old. So Rust avoids that. Named editions, you can name them and you can use them. You can, of course, if you want to be on the bleeding edge and use the nightly changes to the language does still evolve like many other languages. So what you can see here is I'm building this project. It is not that fast, as you can see. It does take some time. This is a random, I think this is actually the current MacBook that I'm using for this presentation that I did this on. I mean, you can see the amount of dependencies is relatively small, but this is because I'm showing here a version of a simulator that does not have many complicated external features involved. If I include a web server, then of course it can quickly look like something like NPM and you literally get hundreds of dependencies. But what you also see is that those are being compiled. So I'm not downloading binaries from the internet. I'm downloading source code, which reduces one attack vector, obviously, but it slows it down. On the other hand, though, the compiles are, as you would expect, incremental. So the next time you do this, you wouldn't have to wait for all the dependencies to compile, and even your own code compiles relatively quickly. This is actually Interesting when you think about backing this up, do delete the target directories because you get gigabytes of binaries in all those directories if you have multiple Rust projects on your SSD. Testing, unit testing, I'm not going to talk much about it or anything at all, really. I'm a huge fan of it. It's actually built into the language. And here, if I go back, you could see that's actually really fast. You can see the build is almost instantaneous here, and then it runs through. And there you can already get a first glimpse of the speed. And I would say I'm a person who practices almost always, both in my hobby projects as well as at work, test-driven development. And the compiler speed, even though it felt a little bit painful on the last screen, has never really gotten in the way. I'm quite sensitive about having a flow. I don't like waiting when I'm doing TDD. I want to write a test, see it fail, write some code, see the test pass. And because of the incremental compiler and how the IDEs work, I've not really felt that Rust is getting me out of that flow. So that works quite well. Now, let's get into some real code. First, let's look at Rust a little bit more from a, how should I say, object-oriented perspective. Rust isn't really an OO language. What we can see here in the first few lines from 15 to 22, we can see a structure that's just the memory layout of a number of variables. It could be considered an object, but it is actually just the memory layout of the data type. There's no behavior attached to it. That comes in line 24, where I'm attaching an implementation. This is actually the structure for the world that we're simulating. But I could just really leave it as just a structure, if you know C, in that world, and not attach an implementation. The first thing you might notice is the brevity. It is not called implementation, it's impl. It's not public, it's pub. It's FN, not function. That is something that is idiomatic in Rust. People really like these short keywords, these abbreviated keywords. And the code I wrote, you can see this in line 25. I'm actually beginning to adapt it. I'm calling it params and not parameters and so on. I've written different programming languages like Objective-C, where you couldn't have a broad enough IDE window. Swift is similar like that as well. But in this case, I think it is actually worthwhile to just accept it as part of the language. One thing that is more exciting is here in line 16, Rust does come with an options type. So rather than having null pointers, that's not possible in Rust, like in many other modern languages. I cannot have a null reference. If I have a string, the string is an empty string, but it can't be null. But I do, like in, I don't know, where you know it from, maybe Scala, you do have an option type, and name can either be none, which means I don't have a string, very explicit, or some, and then that is the string. This is here the name of the world. I'll come back to that much later towards the end of the presentation. Then here in line 25, this is the closest I would say Rust has a convention for constructors. So I'm declaring a public function that is called new. I'm passing in a name. Look beyond the ampersand str, which stands for some kind of string. And then I'm passing another structure, a param structure that is called params. The return type here is world, that is shown by this arrow-like symbol. I guess that's also relatively common. Returns a world. The actual creation, though, Rust has special syntax for it. And you can see this in the green box now. This is how the actual memory is allocated. So here I am creating the world, but that constructor thing is generally used by almost everyone. Look over the name to owned and so on, but basically what you can see here, I have to initialize all the fields that you can see in the structure. I can't leave one of them off. What is interesting here in those lines with random and log, so that's a random number generator and something where I can log statistics to, it uses that constructor syntax. These classes, even though, as I said, they're not really classes, they use that same convention. But another thing that is interesting about Rust is it is really there for the long haul, for large code bases that last for a while, where people can actually put in the effort to understand, yeah, how should I say this? Where shortcuts are worth it. And you can see this here in those lines. I'm saying just params and terrain, but what does that mean? In the lines above, it's clearer, or below, cycle, :0 means I'm initializing the field cycle with the value 0, because as you can see in line 20, it's a U64, an unsigned 64 integer. What does params and terrain do? Here we have a shortcut. It's basically a shortcut for saying terrain: terrain. So I want to initialize the terrain field of the structure with the local variable that I've declared in line 26, terrain. Similarly with params, the one that I'm passing in as an argument to the function in line 25. You could argue that's a meaningless and, I don't know, superficial shortcut, but that is something, again, to know about Rust is it is really there for people who write a lot of Rust code and make it easy, even though for your first encounter with Rust, it makes it more complicated because you have to learn and at least know about these shortcuts. To give you the simplest flavor of how that slightly object-oriented look would look like, here is a method from that same structure, from that world structure. This is a method or function that would run a number of cycles of the simulation. And you can see the first thing here, I'm passing self in. This is like languages like Python, for example, where the instance that is passed in, where it is explicit that you're passing in an instance. In most languages like Java and so on, self is just ambient. It's just there. You can refer to it. Here, I have to pass it in. And even more so, but I'll come back to that later, you have to say that you might actually change it. The other one, I guess, is more obvious. I'm passing in a number. And other things you can see here in line 158, you can see that 0.num, so ranges are first class citizen, ranges are a type built into the language. You can, of course, guess that the underscore in the for loop is there to say, normally a variable would be here, but the compiler would tell me I'm declaring or making available a variable I'm not using. So I'm telling the compiler with the underscore, it's okay, I don't want the variable. And you can then see I can call a method on myself. That's probably the simplest thing you can actually imagine. And I guess even if you've never seen any Rust code, that makes sense. It is actually not completely inaccessible. It appeals to people who have seen Java, C, that kind of language style. It does have a more, and I'm aware of where I'm speaking tonight, it does have a more of a functional side to it. I'm only going to show you an overview or just to show you that they treat that with the same level of syntactic sugar as they do the object-oriented side, namely without very much syntactic sugar. As you saw, you had to pass in the object, and we have to do some legwork. But before I do that, I want to also offer you, I don't know, a little glimpse into how extensible it is as a language. So this function up here, I don't want you to read that just yet. This function here should return the amount of program cycles that are needed to execute a program. And you can see that I'm passing that program in here, which is a list of instructions. You can see those angular brackets and instru. So it's a list of instructions. And I'm passing the parameters, the world parameters that define certain things into this function. And the function should return an unsigned 64. That is the number of cycles that are needed to run this program from top to bottom. How do those instructions look like? What is that data type? And basically, I want to have a hash map that says how long each instruction takes. And you can see this here in line 72. Each instruction should take 10 cycles. The move instruction, they're deliberately chosen to be 3 letters here. The move instruction should take 5 cycles and so on. This is, of course, a literal hash map. But the funny thing is, this is not part of the core Rust syntax. This is actually something that is it's an external library. And if you spotted it earlier, I declared a dependency on maplet. And you can see that the macro system allows me to create completely new syntax. That poses an interesting challenge for some of the IDEs because the language is so extensible that they can't really parse it. What you can see is here, IntelliJ is falling back to saying, hashmap bang, that's a macro invocation, and I can recognize some numbers and commas, so I'm giving them different colors. But this is not Rust syntax. I can extend the language to the level where I can have source code that wouldn't compile with a normal Rust compiler in here. That is, again, a powerful feature that makes it harder for developers who just get into the language. But once you have a larger code base where you need those levels of abstractions, you have them. And I guess many of the programming languages that have been successful did have a powerful macro system. The good thing about the Rust one is it is actually type safe and it can be checked at compile time, and it can even interact with the AST, with the abstract syntax tree at compilation time. I can't go into more depth on this one, but it's actually a super exciting feature of the language. Here, coming back to the functional aspect, I'm basically prog is the list of instructions. I can iterate over them, and then I can do a basic left fold here, starting with 0 as the accumulator. And here you can see the syntax for anonymous functions. ACC, the accumulator, and the instruction are the values that are passed in between the bars, and then following without any further return statements or semicolons or anything, just the body of the function to say the result of each step going through this in the fold is the current value of the accumulator plus however many instructions the current instruction takes. Rust, again, does have a lot of syntactic sugar in the space like this. What I can see here is I can see at the very end, in the earlier bit, rather than doing a generic left fold, I can do a map. And now, of course, I don't have to worry about the accumulator. I'm saying I want to map from one value to another. I want to map from an instruction to the number of cycles it takes. So I'm going from an array of instruction to an array of unsigned 64. And then I can use something like sum at the end. So again, I can chain this. This is exactly what you would expect in most functional programming languages, but it is also, I guess, par for the course in most modern programming languages anyway. A big thing in Rust is the memory management. And I guess that shouldn't come as a surprise, given how I started this talk, saying that a lot of people, a lot of organizations are drawn to Rust because of the memory management. So let's delve into that. The examples here, and I've chosen a different background color, so it's obvious, they are straight from the Rust book, which is freely available on the internet, and I can recommend it as a great resource to not only reference or to figure something out, but I also found it quite helpful as somebody who has programmed in multiple languages to actually get started and learn Rust. So what we can see here is we can declare a string that has the value hello. If I look further at the bottom here, I do the same thing. I declare a string S1, and I'm trying to assign S1 to S2, and then afterwards, in that last line, I'm trying to print S1. That actually does not work in Rust. Because in that line where S1 is assigned to S2, the ownership is transferred. So there is a clear rule that the variable that is bound to this string owns the memory. And when I'm doing S2 is assigned to S1, I'm transferring the ownership. I can use S2 afterwards, but S1 can't be used anymore because it does not actually own that string anymore. It becomes an invalid reference, and the compiler will actually say this doesn't work anymore. Which means, I guess, I'm not sure whether that's clear to you, it is lexically scoped. You can see this in the brackets at the top. The moment I'm actually at the closing curly brace, the compiler knows, because S is lexically scoped to this block, that nobody has any reference to hello anymore, and therefore it can reclaim the memory. It does not need a garbage collector. It does this lexical scoping. It's actually a little bit more complicated, but stick with that for this talk. So how does it work then? So let's go with this. I want to have functions. I want to have methods. I want to calculate the length of a string. Of course, that is built in, but as an example. So here, if I were to pass S1 into the function, I would transfer ownership. And that wouldn't really work very well. So what I do is I'm using this ampersand. And for those of you who have programmed in C or C++, you will recognize this. What it's doing is it's saying, do not pass in the value, do not transfer ownership, merely pass in a reference to this object. So the ownership remains at the site where S1 is declared. It will go out of scope when S1 goes out of scope. That is when the memory will be reclaimed. The function call, of course, is finished at that point. So it is safe to pass the reference into the function. That calculate length, of course, returns just another integer type. There's lots of integer types. You'll get to love them. And returns. So that works. For those of you with a slightly malicious or hacker or security-minded brain, you're probably starting to think, how can I exploit this? But let's first, for those of you who don't know these things so well, look at what it really means to have that ampersand here. And by the way, this is for illustrative purposes only. This is not how Rust works. This is not how C works. And it is not how it works on common CPUs like Intel, AMD, or Apple Silicon. It's just an example. But what you can see here is an idealized version. On the leftmost side, you see memory addresses. Then you see the bytes in memory. And on the right-hand side, you can see the ASCII version of the bytes you see in the middle. So when I'm doing this, when I say let message equal, and I'm getting the message from somewhere, I get the ownership transferred, message now is a pointer to this memory address, to 69674 that you see at the left-hand side of this yellow box. And the letters in there that I framed They are the actual message. That's what this means. What it means owning the memory. And as I said, when message goes out of scope, the compiler knows, and the runtime system, therefore, that memory can be reclaimed. So what does it now mean if I'm saying let message ref being a reference to this message? In languages like Java, Clojure, Kotlin, you don't have to think about it. You can treat them interchangeably. In a language like this, you at least have to know what is happening under the hood. And what that is, of course, message ref also occupies some memory. And I've done this in pink here, and the memory it occupies would be the address 69674, the address of where to actually find the thing. So when message ref goes out of scope, only those 4 bytes will be reclaimed. The message itself not, because I'm only throwing away the reference. When message itself goes out of scope, then, because it is not a reference, it is the actual content, then I can reclaim all the memory for the string. I hope that made some sense. So the next thing here, so now what I do, I'm again declaring a string, s, I'm passing it to a function that is called already ominously change. I'm passing in a reference, and then in that function, I'm trying to change the string. I'm getting that pointer and I'm trying to change it. The Rust compiler will not let me do this. I'll say, this is just a string. You get a reference to it. You can look at it, but you can't touch it. You can't change it. To be able to do this, I need to make 2 changes. I have to first, and you can see this in the declaration in the main function, I have to first say the actual string is a mutable string in the first place. If I don't put MUT for mutable in there, the strings are immutable. Great potential for performance optimization, obviously. But then that mutable needs to go through many places. I have to say, when I'm calling the change function, I want to hand out a reference not only to S, but I want to hand out a reference that can be mutated. I could keep S mutable in my main function and give it to another function without the mute keyword, and then that function would only be allowed to look at it. If I want to pass a reference that can be mutated, the object itself needs to be mutable, and I need to pass it explicitly. And then you can see the change function now says, I not only want a reference to string, I want a reference that is mutable, and then it is allowed to change it. And now maybe you're thinking, okay, what about memory safety? What about handing out multiple mutable references? Let's do this. Let's have R1 and R2, and they are both mutable. And now I'm handing R1 to one thread and R2 to another thread, and mayhem occurs because I have no idea anymore what those threads are doing and what will happen to the memory, who is overwriting what. Luckily, that actually doesn't even work. It doesn't compile in Rust. You cannot hand out more than one mutable reference. You can hand out one and only one mutable reference to anything. What similarly doesn't work is this here. You can hand out multiple references that are not mutable because the compiler can keep track of that. And if all the references you handed out are immutable, nothing can change because nobody can change the variable. So I can have R1 and R2 that are immutable. But then if I try on top of the 2 immutable, or 3 or 4, whatever, to try to create one mutable reference, again, the compiler will not allow this. So the rule is very simple. I can have any number of immutable references or one and only one mutable reference. Makes a lot of sense, right? Because it avoids pretty much all sorts of memory problems that you would otherwise find, especially in multi-thread scenarios. If you think back to what I said earlier on about the automotive industry, in safety critical systems, there's certain standards and levels of safety criticality. And from a certain level onwards, you're not allowed to do pass by reference at all anymore. They say, yes, the C language supports it, but you're not allowed to do it because as humans, we can't keep track of all those references. You must pass by value. But passing by value, of course, is expensive because you have to copy the value all the time. In Rust, the system is such that the compiler can keep track of it. So that class of problems we messy humans can't even create. The last thing I briefly want to show you is this one here, dangling pointers, also very popular. So I have this function dangle. I'm declaring a string s, which is now lexically scoped to the dangle function. I'm trying to return a reference to S, and the compiler will not allow it because, of course, it can see that at the end of the dangle function, S would go out of scope, the memory would be reclaimed, and any reference to S, of course, would be pointing to whatever is in memory at that point. So it doesn't allow that either. There's many other areas where the compiler clearly, again, can avoid us creating problems that other languages allow us to do. So that looked all right, didn't it? I mean, some simple rules. You probably had an intuitive feeling you don't like the rules, but we all understand they are sensible and they help us write better code, and they seem very simple. What I want to show you now in the next 3-4 minutes is what that actually meant and what profound impact those seemingly simple rules have when you're writing anything that doesn't look like Hello World or like the examples from the Rust book. So what are we looking at here? This is the beginning of a function from the terrain. This is also part of the simulation. The world has a terrain that the creatures can run around in. And here this function, you hopefully guess by name, do with creatures mutable, says, dear terrain, do the function that I'm passing in, that function f, or actually the function func as it is called, that function, apply this to all the fields or all the creatures that are on the terrain. I'm using here an object-oriented programming style, so I'm passing in self as well. And then you have f. What is this f thing? And this is something that I personally saw at first in C# as a programming language. Rather than having to specify the generic type in all those places, repeated but also long, I can actually create this kind of temporary alias just for the method declaration. And I can say on the next line what f really is. So f has no real further function. It's a kind of a generic on the method, and I can describe on the next line what it means. And what f is a function that takes a number of parameters. It takes a terrain that it needs to mutate. Think about the case where a creature dies. The creature needs to be taken off the terrain. So the terrain needs to say, okay, the function you're passing me, I'll give you a terrain that you can change. The next thing the function can do, it takes a creature. And then you see another nice bit of Rust syntax. You can have tuples. So again, another generic data type, not generic in the sense of generics, another standard data type, first-class data type that is built in. Here, a tuple of 2 unsigned 32-bit integers. And it returns an option of a tuple. And basically what that is telling this function, this is the position, it's a grid, where that creature sits at the beginning. And the function can say, after it executed, this is the new space where the creature is, because it has moved. Why is it an option? Because the creatures can die, and then it would return none, and the terrain would know, okay, that creature is no longer in the terrain. Makes sense so far, right? So this is what I want to do. This is the API, if you will, that the terrain offers. I can tell the terrain, do something with all creatures. I'll give you a function, and the terrain will make sure that that function is called with all the creatures that are in the world. Let's look at the call side now. How does it look from there? This is in the world. It's called process all creatures. And you can see there in line 137, it says self.terrain. So the terrain that is attached to the world, do with creatures mutable. That's the function we just saw. And then we can see the anonymous Clojure that is being the block that is passed in. We're passing in the terrain, the creature, and the position, and we do something with it in that function. And you can see this here, for example, in the first line, in line 139, I'm decreasing the energy points. I'm taking away 1 energy point. In the next line, I'm checking, is the creature's age larger than the maximum age as defined in the world parameters? If that's the case, or, the double bar is an or, like in many other programming languages, if the energy points are 0, I'm returning none. That means the creature is either too old or it ran out of energy. And then it is taken off the simulation. That looks actually quite nice code. This is exactly how I wanted it. Nice separation of concerns. The terrain knows how to iterate in the reason why it's done in the terrain is because it knows its data structures and can do it very efficiently. These simulations want to run fast. But I can have the logic that needs to apply what the world needs to know about in the world. I mean, of course, I could have created another named function here. It didn't have to be an anonymous function. But I mean, I felt the separation here was clear enough. What I guess you don't expect is this doesn't compile. And this is the actual error message that the compiler spits out. It is that long, and it does include the ASCII art. In the beginning, and I've talked to many people, I've given this talk several times, almost everybody feels like overwhelmed by these error messages. But again, this is a language that is in there for the long run to support you in complicated situations. And once you've gotten used to this ASCII art, it is actually really, really helpful. It allows you to see much clearer where the problem occurs, especially, and you will see this in a minute, when you have these complicated back and forth between different rules of memory management in this case. What is also interesting, you can see this at the bottom of the screenshot, the errors are numbered. So this is 0500 and 0501. You can call the Rust compiler, have it explained. It's also a hyperlink and it gets you to a website, a web page that will show you more details. So again, here the ecosystem is super helpful. The Rust people know they have created something that is not that easy to learn, that does have a learning curve, but they're doing everything they can to actually make sure that somebody who's learning the language has the best possible chance of actually getting over the learning curve without having to study on their own for several months. I'm very impatient. I mean, I only started reading the book and then immediately took this. I'd actually written, and I'll come back to that later, I'd written this simulation in Clojure first. And when I wrote the Clojure version, it was actually great fun to write it. But yeah, we'll come back to that later. I had reasons to actually try this in Rust. So what is really happening here? So we're seeing here again from the previous slide, the block that I'm passing into this function. But what I'm doing here, look what's happening. I'm saying in that anonymous function, self.params.creatureMaxH, I'm capturing something from outside the block. The same is true for self-cycle. But I am not allowed to do it because here I'm doing self-terrain. With self.terrain, I'm already borrowing terrain. I'm basically saying self is now used as a reference. And therefore, I can't have further references. And that's what the error message says. The Clojure I'm passing in requires unique access to self because here self is mutable. It needs to be able to change, but I can't because I've already used terrain. The surprisingly, at least for me, simple solution was to do it like this. You just pull out the values, self.cycle and self.params, into local variables. And now it works. Because now, when I do self.terrain, the borrow checker can say, okay, self is now borrowed. I can't do anything with it anymore. But the Clojure that I'm passing in does not have a reference to self anymore. Semantically, of course, there is a difference, right? In the previous one, if in line 143, self.cycle had been changed somewhere, the Clojure would have seen it. But here in the bottom one, in line 145, I'm saying cycle, and that captures the local variable declared on line 137. The point, though, is the compiler and the memory system has actually made me do the right thing. I actually want the snapshot at the beginning. I don't want, if anybody else changes, to see that change. So it basically, through the memory management rules, forced me to snapshot the value in a local variable, and the Clojure then knows clearly what it does. I don't know whether you've seen this before in other programming languages, especially when you're working with multi-threaded code. This can be a source of really, really hard to trace problems, that a value that you get as a reference is changed somewhere else, especially in combination with captures into closures like this one. If you have done Swift, you will know that they have escaping and non-escaping closures to tackle this. I must say, after some cursing in the beginning, I find the Rust approach in the end more effective. If it's more elegant, I'm not sure. But it's very clear. Last thing that I want to talk about, actually the last language thing I want to talk about, and after that I want to talk a little bit about performance, is parallelism. Because Rust is so clear about how the memory is owned and when it gets released and doesn't need a garbage collector, multi-threaded becomes a non-issue. It just works. And what we can see here is, if you think about this, I told you that this is about a simulation system, and it can run multiple simulations in parallel. You have to trust me, if you've built something similar, you can probably confirm this. There's no point in running a simulation like this itself on multiple CPU cores. The overhead would just be inter-thread communication would be too expensive. But what I want to do is I want to run many of those simulations, and rather than running sequentially, if I have a CPU with 4 or 6 or 8 cores or more, I can run multiple simulations in parallel. So this is what this function does, run multiverse. And what you can see here in the first line in the method description, the world function, that's a function that creates a new world that is to be simulated. Here you can see I declared a function inline. I didn't use that syntax where I declare the type on the next line. And you can see it's very simple. It's a function that takes no parameters and it returns a world. It's basically a generator function, right? And it has some internal state to actually know what kinds of world to create. Oh, yeah. What I'm then doing in line 25, I'm basically iterating over the number of threads. That's a constant on this machine. Where I first did it, I said I have 8 virtual, with the hyperthreading in the CPU, 8 threads. So let's keep 1 so I can actually still use the computer and use 7 threads to actually run those in parallel. And then in there, I'm doing thread.spawn, and I can just pass in, again, an anonymous function that is actually then the starting point of each thread. The only thing that you need to know is you can see the keyword move there, which signals to the compiler that you want to move the ownership of certain values into this other thread. And again, then there's a lot. Actually, you can't do anything with anything that you haven't captured in that way, because the compiler, of course, will smell that there's many, many issues if you try to access variables from 2 threads in parallel. World function, of course, works. I'm not passing a world object. I'm just passing a reference to an immutable function. It is only the function, when I invoke it there in line 28 with the round brackets, that it actually at that point in time, but already in the thread itself, creates the actual world structure. Trying to create the world outside would have been slightly more difficult, although I could have also used move to move it in. People have told me that the double bar looks a bit weird. What is this OR thing? It's not. It's just an empty parameter list. If you remember that from the earlier examples, a bar and then the names of the parameters, another bar is how you do anonymous functions. Here, I'm not passing anything in. That's why you get this funny double bar. For the last bit of code that I'm going to show you, this is interesting. So when I'm spawning a thread, I'm getting back a handle. And you can see in line 23, I'm declaring handles as a vector, as an array of handles, and I'm just pushing that onto it. And it uses the same thing as many languages have. You can use an array like a stack if you just call push and pop and you add at the end and actually take from the end. That's not so exciting. What is more interesting is how all of the, or not all, but many of the things I showed you actually come together quite nicely. And you can see this here in line 34. I'm doing handles.pop. And most programming languages that have a stack, of course, need to somehow signal the stack is empty. How does Rust do it? It uses options. You might have, if you know languages that have options, you have seen this. So you either get some and then a value of the type that the array is, in this case, a handle. You actually notice that I'm not specifying it. It's done completely through type inference. You can't see at all in this code what the type, it's never spelled out. But the compiler, of course, can ensure the safety because it knows in line 26 what thread.spawn returns. That is enough of a hint that it knows everywhere else what the type is. But that's beside the point. What I can then do in line 34, I can use destructuring. I can say sum of age, and that age then is only assigned to actually a handle if pop returned not none, if it returned some. If pop returned none, then the let will not work and the while loop will terminate. So again, it looks a bit weird if you have not seen this kind of code before, but it really brings together a lot of these concepts quite nicely. And it shows you that once you have mastered these different aspects of the language, you can write some really relatively clear code, right? I mean, in many other languages that have null pointers, you would have to somehow check, is it a null pointer? And then you might use a for loop. Other languages that don't have null pointers but don't have options, you would have to first ask handles, do you have elements? Because otherwise it might throw an exception. But here, that combination of options with the destructuring and the while let loop actually creates for some elegant code. So then, I'm almost over time. Or actually, I'm over time. So I don't want to bore you too much, but I do want to talk very briefly about performance. I mentioned this before. This actually is running here a visualization of a simulation, of course, slowed down dramatically, but you can see these little yellow creatures running around and the green dots are the food that they can consume. And as I mentioned, I think the first version I wrote of this was in Clojure. And when I timed it on the machine at the time, it could do about 110,000 cycles per second. So a cycle is, as we saw early on, like a command or a subset of a command of one of those creatures. That was okay. I was actually surprised how fast it was in Clojure, but that speaks to the quality of the Clojure implementation and especially to the quality of the JVM. However, to run those simulations, it wasn't really fast enough, and that it is a hobby project. That's why I lost interest. The simulations were running too slowly. I was basically still stuck in finding the right hyperparameters for the simulations, and it just took days and days and days to actually run enough simulations to get a good understanding from an experimental point of view. And that's why I left it aside. And when I decided to learn Rust, I thought, oh, I want to come back to this hobby project, because even though I liked the implementation in Clojure, it was too slow, and Rust had this idea of being faster. So I basically took the acceptance test, copy-pasted them from the Clojure source code into Rust, changed the acceptance test, the Clojure code, until it compiled into Rust code, and then implemented the Rust function. So it is actually really a one-for-one thing driven entirely by the acceptance test. And they were really with high coverage because I drove the entire Clojure implementation from those acceptance tests. Running this in Rust gave me this 3.5 million cycles per second. So that was a speed up a little better than I'd anticipated, but roughly in the order. I mean, I had done enough C programming, Objective-C especially, to actually see that there could be more into it. But then at some point, I don't know exactly, I think when I used the profiler, I remembered, because it was mentioned there, to run the profiler or the debugger also, to run them either with a debug compiled version or release version. I was like, oh yeah, shit, what did I actually do? And I realized that when you compile Rust normally, it actually runs with a lot of debug symbols and also a lot of debug code enabled for array. For example, bounce checkers on arrays and all sorts of other things to make sure. You can also, of course, once you're satisfied that that your code works, that it passes all the tests, you can do a release build. It takes longer to compile, like in most languages, but the compiler does some heavy optimization. It can also lean on the tool chain that is not all Rust specific. At the bottom, it uses Clang. That's the same tool chain that is used by some versions of C++, but also Swift, and can actually optimize quite aggressively. And I did that. And when I ran it, I got this. So I got to 25 million cycles per second over 110,000 in Clojure. And that is roughly giving us an idea of a really good JVM language. And I think I'm I'm an okay Clojure programmer. I didn't make any stupid mistakes, but you can still see the order of magnitude difference or orders of magnitude difference you can achieve by having a language that is really so much closer to the metal of the CPU than a language that is in the end still running on a virtual machine. One thing I do have to say as a last remark is, in all fairness, in Rust, I did some profiling, and I realized that at some point it was spending about half the time in the random number generator. The random number generator that is the standard in Rust is cryptographically safe. That's a good choice, I think, because often problems in crypto libraries occur because the numbers are predictable. But for deciding whether a creature wants to turn left or right, or how I splice their programs together, I could have a very much simpler random number generator. So I switched to a simple XOR shift random number generator, and that gave a speed up of almost 100%. It halved the runtime of the application. So in all fairness, I didn't check that with with Clojure. If I go to the Clojure version and change the random number generator, that might give some speed up, but certainly not in order of magnitude. That's it. Thank you for listening, even though I went over time a little bit. If you like this talk, there is a very similar version of the talk available on YouTube, and you can find it by searching for those words. Thank you very much.
Thank you very much, Erik. Very interesting. Super interesting. I have there's no questions yet in the chat. I have a question though. What was the idea behind this simulation? Did you have any research project or any kind of hobby research you wanted to do with it?
Yeah, it started. I mean, it's interesting now. Everybody talks about deep learning and neural networks. I studied in the 90s, in the early 1990s, and that was when neural networks were also pretty hyped up. There was a winter before that, an AI winter, and then in the 90s, people looked at neural networks again, but also saw that neural networks were good for certain things, but not for everything. And then they also looked at genetic programming. And as students, we had to do a project where the professor said, combine genetic programming with artificial life, which was also a big thing at the time. And we did this, and the machines were utterly slow, and it was really painful. And we wrote this in C. And then years later, I thought that was actually a fun little thing. And I don't know, I had enough times sitting on trains or in hotel rooms as a consultant. So I programmed that. I revisited that and wrote it in Clojure. And I could basically replicate in many of the examples we had done as university students.
Interesting. Would you say like code-wise, because you're written it first in Clojure and then you're written it in Rust, and it apparently is, of course, as when you come close to the bare metal, it's always going to be faster. I mean, that's just the natural thing. Would you say, like from a coding point of view, what would you say with the difference? Is it harder to write in Rust, or is it just that you have to learn Rust or Clojure, or what would you say there's like differences there?
I mean, the first thing I can definitely say is the Clojure version was more fun. I enjoy writing the Clojure version. And also I don't know how about you, but sometimes as a programmer, I find I get some satisfaction. I look at some code and I think, that looks neat. It's a
Yes,
great solution.
I agree.
And that I had way more often in the Clojure version. In Rust, it was a bit more wrestling with the compiler. In all fairness, though, I mean, I knew Clojure before I wrote the Clojure version, and this was my way of learning Rust.
Mm-hmm.
But still, in the Rust version, it was more like, if it passes the acceptance test and I get the compiler to compile the thing, it's probably right. But I didn't get that sense of achievement, right? It wasn't like I thought, okay, that's really nice. It looks beautiful. It doesn't look ugly, don't get me wrong, but it clearly wasn't as much fun. What is more readable? It depends. If you have seen functional programming, I mean, if you've seen Lisp or Haskell, the Clojure version is definitely more readable.
Okay, yeah.
If you're somebody who has only ever done C++ or Java, I'm not so sure. I would still say programmers with experience would probably see more elegance in the Clojure version, but they would find the Rust version more accessible because of the dot notation and so on, the way brackets are, that it still gives you these structures that have fields and so on. It feels more familiar to people who are, as I said, who know Java, JavaScript, and so on. This kind of, I guess you can trace it back to Algol, that line of languages.
Yes. Let's see. I have some questions here. Is the GUI you showed also made in Rust, or is there another front-end language?
No, the GUI is done in JavaScript, actually. It uses D3, which is a visualization library. There is, if you go to this, or if you look for my name, but I think I also linked it in the YouTube comments, you can get the source code, both the Rust version and the Clojure version, on my GitHub repository. So you can see that there. The Rust version is interesting. The version I used for this talk is an older version that is simple, that doesn't have the visualization built in. It's tagged, so you can see the exact version of the code that I've shown in this presentation. There is a later version in that repository that does have the visualization. And basically what I've done is I've made available the data structure that of the simulator is running and serialize it to JSON. And then the UI is running in a web browser, which consumes the data in JSON and then uses D3 to actually render it.
Yeah, cool. Yeah, that was what I'm going to ask, actually, if the source code is available. But you already said it. It's available. We'll link it also in the links later in the below here, so people can find it, of course, for those who are interested. And also, if you're interested, you could rewrite it. Maybe you can improve the performance if you write it in assembler, but maybe you're going to spend the rest of your life writing it. Who knows, you know?
I mean, there was one group who wanted to rewrite it in Haskell.
Yeah.
They have never gotten back to me. In all fairness, I mean, it is not very well documented. It is a hobby project after all. So, I mean, have a look at it. But yeah,
of course.
I wouldn't say I'm a Rust expert. I'm not sure you can learn many neat Rust tricks from it. I just made it available because people asked.
Yeah, I think it's I just got very intrigued and interested when you started talking about this like genetic programming and how things. Yeah, it's kind of a simulation of the real world in the sense. So it gets really interesting. Thank you very much again, Erik, for coming on to funcprog Sweden.
Thank you for having me.
Yeah, you're welcome. And with that, we are ending tonight. Thank you everyone for watching, and we'll publish the 2 separate presentations as like tomorrow or on Thursday. With that said, thank you very much everyone for tonight, and welcome back for the next funcprog Sweden. Goodbye.